Welcome back. The objective of this video is to write an augmented matrix, so we'll introduce you to augmented matrices and a coefficient matrix. We'll talk a little bit about elementary row operations and things that we can do to manipulate matrices to help us answer questions. We'll introduce row echelon and reduced row echelon form. You'll see me abbreviate row echelon form as REF, and you'll see reduced row echelon form abbreviated REF. We'll use row echelon form for our purposes in this particular class. And then finally we'll solve a system of equations using row operations and back substitution. But we will also use row operations for other things, for finding inverses of matrices, and that kind of thing. So row operations is going to be important for our future studies. So just as a matter of definition here in Objective 1, I've got a system of equations of three variables, x minus 4y plus 3z equals 5, negative x plus 3y minus z equals negative 3, and 2x minus 4z equals 6. And what we do in a coefficient matrix, we end up dropping all the variables and working with just the coefficients. So in a coefficient matrix, I'm going to write down my coefficients for x, y, and z in their rows, and then for each equation. So equation 1, equation 2, equation 3. In an augmented matrix, we do the same thing. We still use our coefficients, but we bring our constants then down and create a fourth column with our constants. So now we have our row 1, row 2, and row 3 with our x, y, and z, and then the constant value that's not involved with the variable. So that would be an augmented matrix. We'll see different kinds of augmented matrices when we do further videos and further studies. But in terms of solving a system of equations, this is going to be our augmented matrix. In example 2, we're going to introduce elementary row operations. And we can do this for an augmented or coefficient matrix. But row operations allows us to it produces equivalent but new matrices. And this helps us solve a system of linear equations. So two matrices are row equivalent when one can be obtained from the other by a sequence of elementary row operations. So you can interchange two rows, so we can swap rows out, that's no problem. We can multiply one of the rows by a non-zero constant, and we can add a multiple of one row to another row. So when we did the elimination method of solving systems of equations, we did this kind of thing. We did multiply one row by another and we added them together. So this is a process that we've done before, and it's going to be very similar to what you see when we do our row operations. Here in Objective 3, we define the difference between row echelon and reduced row echelon forms. Row echelon form has the following properties. Any rows consistent entirely of zeros occur at the bottom of the matrix. For each row that does not consist entirely of zeros, the first non-zero entry is always 1, or for the leading 1. And for two successive non-zero rows, the leading one in the higher row is further to the left than the leading one in the lower row. And a matrix is in reduced row echelon form when every column that has a heading leading 1 has zeros in every position above and below its leading 1. So something in reduced row echelon form only has zeros and ones in it, and in a particular order. So let's take a look at these 6 matrices and see if they are in row echelon form or reduced row echelon form. From the solution below, we can see that the matrices in A, C, D, and F are in row echelon form, and the matrices in D and F are actually in reduced row echelon form. So D and F are in reduced row echelon form. So The matrices in D and F are in reduced row echelon form because every column that has a leading 1 has zeros in every position above and below its leading 1. So we can see above and below its leading 1, we have nothing but 0. So those are in reduced row echelon form, where like A is just row echelon form, because here in column 2 we don't have a 0 above the 1 in row 2. And we've got a negative 1 up here. So this one's in just row echelon form and not reduced row echelon form. This one is in B is neither, because of the zeros is not in the bottom row. C, we said that one is in row echelon form. And row echelon form, you can see our 1s kind of go on a diagonal, and we've got all these zeros here, but we don't have all sorts of zeros up here like we do in these guys in D and F. And then E is also neither. In Objective 4, we're going to solve a system of equations, and we're going to use an augmented matrix and row operations to solve the system of equations in 3 variables. So we're going to drop out the variables and keep the coefficients and write our augmented matrix. So I've copied the information down. I've simply dropped the variables out. I have a column of x's, a column of y's, a column of z's, and then my constants. And if a variable is missing, we would just put 0 as a placeholder in that spot. So we kind of have our equation 1, equation 2, equation 3, and our x's, our y's, our z's, and our constant. Next, we're going to complete row operations until the matrix is in row echelon form. So our goal is going to be to get a matrix that looks something like this. So we have 1, 0, 0 here, a 1 here, and a 1 here. So we don't really care what the numbers are to the right. We're going to use those, of course, but our goal here really is to get this corner, this top first row, first column as a 1, second row, first column as a 0, and the first 2 columns in row 3 to be a 0, and these other coefficients to be 1. So that's really our goal matrix. So I've recopied my original augmented matrix down. I've dropped the colons here. You don't really need those. And we want to start really by getting this second row, first column to become a 0. So I want this negative 1 here in the middle row to become a 0. I want that spot to be a 0. Well, if I add the first row to the second row, 1 minus 1 will be 0. So that's what I'm going to do. And I'm going to note that by saying I'm going to take row 1 and I'm going to add it to row 2. So when I add row 1 to row 2, row 1 will revert back to its original values. I'm really not changing it. In other ones I'll change. And row 2 will take on new values. So let's see what that looks like when I add row 1 to row 2. So I've added row 1 and row 2 together, and I've created my new matrix, matrix B. My top row stays the same at 1, negative 2, 3, 9. My middle row now becomes 0, 1, 4, 7, and of course my bottom row stays the same at 2, negative 5, 5, 17. So now my next goal then is to change this 2 to become a 0. I would like this guy now to become a 0. That's my goal, because I'm building this corner down here to be zeros. Well, if I take row 1 and multiply it all by negative 2, and I add it to row 3, right, this 1 will become negative 2 plus 2 will become 0. Negative 2 times negative 2 is 4 plus negative 5. So when I do that, as I have in my instructions over here on the right hand side, negative 2 times row 1 plus row 3, row 1 will revert to its previous values, and row 3 will take on new values. So I'm going to do -2 times row 1 plus row 3. So my new row 1, that would become -2, that would become 4, that would become -6, and that becomes -18. That's my new row 1. I add it to row 3, and I'll get a new matrix where my top row stays the same, my middle row stays the same, and then my bottom row, my new row 3, so -2 plus 2 is 0. 4 minus 5 is -1. -6 minus 5 is -1. And -18 plus 17 is -1. Now we could multiply all of these by -1 and turn them all into ones, but we don't need to do that right now. Our goal is to make this spot here now, we want to get this spot to become a 0. That's our goal. So if we simply add row 2 to row 3, that will become a 0, and let's see what we get when we do that. So we're just going to take row 2 and add it to row 3. So you'll notice here that what we're adding to always becomes our new row, and all the other rows go back to what they were. So in our matrix D now, row 1 will stay the same, row 2 will stay the same, and now row 3 will take on those new values. So row 1 and 2 are the same, then row 3, 0 plus 0 is 0, 1 minus 1 is 0, 4 minus 1 is 3, 7 minus 1 is 6. The only thing I'm missing here is a 1, and that is very fixable because I can multiply this third row by 1/3, making that 3 a 1, and this a 2, and I will be in row echelon form. So my final matrix E here, when I multiply this row by 1/3, row 1 stays the same, row 2 stays the same, row 3 then becomes 0, 0, 1, and 2. And now my matrix is in row echelon form, and I am ready to do back substitution to solve my system of equations. Now remember, my x column, my y column, my z column, and my constant, so you can probably see here that z has to equal 2. So now I can do my back substitution. I'll show you how that works. So I've just copied over my matrix, again, my x, my y, my z, and my constant. So working from bottom up, I can say z equals 2. So from my middle row, again, I could say 1y plus 4z equals 7, but since I know z equals 2, I'm doing my back substitution. I can say 1y, and you won't write in the 1, plus 4 times 2 equals 7. So now we know that y, subtracting 8 from both sides, we know y is equal to -1. And then from our top row, we know that x minus 2y plus 3z is equal to 9. And we already know our z and our y, so x minus 2 times -1 plus 3 times 2 equals 9. So this is back substitution. We're substituting back into the equation and solving for our variables. So we get x plus 2 plus 6 equals 9. I subtract 8 from both sides, and x is equal to 1. So we have an x value, a y value, and a z value. We'll write that as an ordered triple, x, y, z. So our ordered triple here is 1, -1, and 2. And order does matter, so make sure generally alphabetical order in these kinds of problems, but definitely the order that you have them in the equation. And there is an example of row operations and using back substitution to solve a system of equations. We'll use row operations for other things with matrices, and you'll get some more practice with this when I see you in class.